Okay, last lecture of the unit. It's a big one. It's a really, really important one, and it's over periodic trends. These are the 4 periodic trends you guys are going to be responsible for. You've covered all of these in your Chem 1 course. The big difference between what you did then and how you're going to deal with it now is the point that you have to explain all of it. There's no longer going to be the easy questions, which is bigger, and you rank things. That might be a part of it, but more importantly is your ability to explain why for all of them. So we're going to go ahead and start with atomic radius. So take a look at the periodic table. I tend to kind of go off page here and focus on the periodic table. I also like to start with going down a column. As you go down a column, what happens to the size? It gets bigger. The question you'll have to answer is, why is that? Any ideas? More shielding. That's actually the perfect answer. Shielding is basically the extra core electrons that are present between the nucleus and the valence electrons. Well, what does that mean? Notice as you go down the table, you're increasing what? Energy levels, right? So as the energy level number increase, watch my hands, it's obviously going to get larger. Got it? So the shielding portion comes in talking about how the ability of the nucleus to communicate with the valence electrons. So if Jessica is a nucleus and Monica's a valence electron, all of you guys, raise your hands up. You're blocking her ability as a nucleus to communicate or to pull on the valence electron. So you guys are shielding her from her. So more shielding, larger size. Shielding is the catchphrase that will get you credit on the AP. I'm kind of teaching to the AP, which is maybe not a good thing in some people's eyes, but I think it is, because you'll get 5s and you'll be like, boo, take that, to everyone else who doesn't get 5s. Ultimately, shielding will get you, by saying more shielding or less shielding, that'll be enough of an explanation for up and down. All right? As you go across, it gets smaller. Why? Okay, I'm going to on the no protons. A bunch of people yelled out no protons. That to me is an absolute farce, because what's happening to protons as you go down the table? More protons. So that argument isn't enough. Yeah, there's more protons, but you're adding more protons to the same energy. The electrons are on the same energy level. As electrons are being added as well, those electrons are being added to the same energy level. So if you look, we're going across like energy level 2. This is it. You add more protons. Every time you add a proton on the same energy level, nuclear pull is increasing, your effective nuclear charge. As opposed to going down the table, you add a proton, we add a level. You add a proton, we add a level. Okay? So the effect of the nucleus is going to be stronger. You're allowed to use the term effective nuclear charge only for going across the periodic table. You cannot use effective nuclear charge as an argument for going down the table, and I'll explain that mathematically in a second, because effective nuclear charge is actually a calculation. But because you're going across, protons are increasing with the same number of energy levels of orbitals, the pull on those is going to increase. Got it? So let's take a look at, I hope you got it because I'm going on. This is just a little pictorial representation of the radii on the periodic table. No biggie. What I want to, though, show you is why effective nuclear charge as an argument has to be used across and not up and down. Effective nuclear charge is also known as Z-effective. You could say ZEFF as well, if you're using it for an argument across. Effective nuclear charge is calculated by taking the atomic number. What's the atomic number? Number of protons minus the core electrons. What are core electrons? Say it louder. Non-valence electrons. So let's just look at 2 going across. Let's compare carbon to fluorine. Which one is smaller? Carbon or fluorine? Fluorine's smaller. So that should have a higher effective nuclear charge, meaning its nucleus should be stronger. So we're going to make sure it's got a higher by actually calculating. So what is the atomic number of carbon? Atomic number of carbon? 6. Now, the core electrons are the electrons on lower energy levels than the valence. So you're ignoring the S&P on level 2. So how many core electrons are there? 2. So carbon has a Z effective of 4. That's a meaningless number unless I have something to compare it to. Let's compare it to fluorine. What's fluorine's atomic number? 9. How many core electrons in fluorine? 2. So what is its Z effective? 7. Fluorine has a stronger effective nuclear charge. Therefore, it is smaller. Okay? You can only do this when you're comparing elements on the same energy level. Okay? Because when we get to, let's do rubidium and let's do sodium. Let's compare their Z effective. Sodium has an atomic number of 11. How many core electrons does it have? Core. It's got 11, so everything up into 10, right? There's only one valence electron, so the rest of them are core. So it's got 10 core electrons for a Z effective of 1. Rubidium, what's its atomic number? 37. And how many core electrons does it have? 36. So you're telling me they're the same size? They have the same effective nuclear charge. No, you can't utilize Z effective when you're comparing things with different numbers of core electrons, okay? Got it? So the questions you'll be asked are pretty straightforward. They're not going to trick you necessarily. Which should be the larger atom and why? Sodium or chlorine? Sodium, why? Sodium has less nuclear pull or a less effective nuclear charge. Sodium has, I guess I should be writing this down since this is a videotape. Sodium, less Z effective, less nuclear pull. Any of these are fine. Less effective. I'm like the guy in the video yesterday. Nuclear charge. Except I'm a little bit faster. Okay. Which would be the larger atom? Why? Cesium. Why? Okay. I'm going to bonk the answer. Shielding as the answer. Which has more shielding? Cesium has more shielding. I need all of that. You can't just say cesium, which is larger. Cesium, because shielding. No. I need you to, when you say shielding, as a grader, I'm going to be like, so is it less shielding that's causing lithium to be bigger or cesium to be bigger? Or clarify. You got to clarify for the grader so they don't have any question about what's in your head. So cesium has more shielding. If you don't like to use the term shielding, I'm okay with that. You can say there's more energy levels in a cesium atom. Don't care which. Either's okay. All right. Now let's look at ionic rate. Is everyone good with just regular atoms? All right. Now, looking at ions. There's lots of different ways to compare ions. And so we're going to just take the different possibilities, compare ion sizes. The first is to compare ions to their neutral atom. For instance, if I had calcium plus 2 versus calcium, which one's going to be bigger or smaller? Well, first thing you need to do is identify what do those two things have in common? Number of protons, right? State that in your argument because that's your basis of comparison. So since they have the same number of protons, the one with more electrons would be bigger or smaller? Bigger. Why would the one with more electrons be bigger? Think about the nuclear pull, that nuclear capacity of that number of protons. When there's more electrons, you can't hold them in as tightly. More electrons can't hold as tightly. So which one has more electrons here? The calcium does. Okay, so that one is going to be larger than the Ca plus 2. So this one's going to be smaller. You could also say calcium plus 2 is smaller because there is a larger proton to electron ratio. You can say that as well. There's lots of different ways to approach this. Okay? The important part is recognizing those two things have the same number of protons. A quick way is to look at charge. The higher the charge, that means there's more protons than electrons, right? So that means the pull is tighter. So if you're comparing sodium and sodium plus 1 is smaller. What if you're doing nonmetals like N and N minus 3? Same thing with the charge. Those both have the same number of what? Same protons. All right? Since they have the same number of protons, N minus 3 is larger because of less nuclear pull. Less pull per electron. Another argument that people use, which is acceptable as well, I think the nucleus has more effect than this does because the electrons are more spread out, so I don't think it's as good of an argument. But you could also say more electrons will have more will be more repelled because they're more electrons. So being more repelled makes the electron clouds bigger. That's an okay argument. But again, I'm banking on the fact that if you got X number of protons and X number of electrons, the more proton to electron ratio there is, the smaller the atom. All right, so that's one way to do it, looking at charge. Another way is just to compare ions in the same family. And I do mean family, and I do mean up and down. So if we're comparing like sodium plus 1 and rubidium plus 1 and potassium plus 1, what's your guess on how these are ranked? What is? Sodium's the smallest. You just follow the normal trend. Okay? Anytime you're going up and down, the level takes the precedence. And this only works specifically with ions if they're in the same family. And I don't know if I spelled precedence right, and I really don't care because I teach chemistry, not English. Okay, now there's two other things you can look at. This is going to look kind of crazy, and you're going to be like, oh, they're everywhere. What's going on? If I were to compare sodium plus to N minus 3 to F minus, you're like, holy crap, what's going on? What you have to do in a case like this is figure out what noble gas these things are isoelectronic to. Then you can rank the noble gas sizes. So what is sodium plus isoelectronic to? Neon. What's N minus 3 isoelectronic to? Uh-oh. What's F minus isoelectronic to? Neon. Ah, crap. What do we do now? Okay. Now we have to look at what's the same about all of them and then make our comparison. What's the same about all of these? And don't tell me number of protons, because number of protons is different. The electron configuration. So what does that mean? We have the same number of electrons. So here we have the same electrons. So what's going to dictate the size in this one? Number of protons. So which one's going to be smaller? The one with the more protons or less protons? More. So the more protons is going to be the smaller one. Which one has the most protons? Sodium is the largest, the smallest. And then? Fluorine, and then? Nitrogen. Okay, and you rank them. It does rank from positive to, the more positive it is, you can also look at that number. The more positive the number, the smaller it is, and then it increases as charge decreases. Okay, because again, it's that proton to electron ratio. Then the final possibility you might run into is when they're really all over the board. Let's say you have barium plus 2, and you have oxygen minus 2, and you have bromine negative 1. Okay? Again, since they're all over the place, and you need a basis of comparison, go ahead and find out what noble gas they're isoelectronic to. Barium is isoelectronic to xenon. O negative 2, neon, and Br minus, krypton. All right, so do you just rank these based on their size, and then that's how you rank the size of the atom. So which is the smallest? We're not looking at neon though. We're going to say O negative 2, right? And then what's next? Br minus, and then the Ba plus 2. So those are all the different possibilities they might throw at you as far as comparing ions. Are we okay? Ooh, y'all convinced me. Moving on. All right, electronegativity. Electronegativity is used primarily when we get to the bonding unit, but I want to introduce it to you and mention there is a trend in the periodic table that fits it. To do this, you need a definition. So electronegativity is the tendency of an atom to attract an electron in a bond. That's the most important. So small noble gases that don't react don't have electronegativity values because like helium and nitrogen and neon, helium and neon, for instance, don't react with anything. So they don't have a tendency to have an attraction in a bond. So think about, I always go back to nuclear pull. What atom would want an electron more? Something with a really strong nuclear pull or a weak nuclear pull? Strong. So if an atom is bonding with something and it has a strong nuclear pull, it's going to be more attracted. So as you go across the table, what's happening to nuclear pull? Increasing. So if it's increasing, what happens to the attraction for the electrons? Increasing. It increases as you go across. As you go down, we're adding energy levels. What's happening to nuclear pull? Decreasing. So as nuclear pull decreases, electron negativity decreases. Case in point, the most electronegative element, who knows it? Fluorine the floozy. And you get to meet her today. There she is. She's got a little cigarette. She's hanging out. For lack of a better term, fluorine is an electron whore. She wants electrons. She is the most electronegative. So when you're comparing different things, the closer something is to fluorine, the more electronegative it is, okay? So, a counter, who's the least electronegative, do you think? Good old francium. Francium the freak. He's up there too. When those two get together, woo, we got a reaction going. He's a little punk rock dude right up there. So francium is your least electronegative. How do we use electronegativity? We use electronegativity mainly to determine bond type, which is all next unit. So I'm going to show you quickly for those of you at home. Sorry, you're going to be bored. So let's say I'm trying to bond here with Irene. Okay, Irene and I are the same electronegativity, so we're oxygen. She's going to grab my other here. So we're sharing an electron in this bond. Okay, we're both the same electronegativity, happy, sharing the bond. This is a nonpolar bond. Irene will be oxygen and I'm hydrogen. Who's more electronegative? Oxygen or hydrogen? Oxygen. So she is going to be more electronegative. I'm losing my electrons a little bit, but I'm still sharing them with her. So we're still covalently bonding, right? But they're closer to her. So what kind of bond are we? Louder. Polar. We're a polar bond now, because now she's partially negative, I'm partially positive, because the electrons are closer to her. So now we're going to be sodium chloride. She's chloride, I'm sodium. Who's more electronegative? Chlorine. She's going to take it from me. Our difference in electronegativity is so high. She not only has her own electron in that bond, she took mine too. So she is an actual ion now. She's a negatively charged ion. I'm a positively charged ion. So how do we bond? Opposites attract. Electrostatic interaction. Now we just attract that way. We're not sharing the bond like that. We're actually just opposite charges that attract. Okay, so those are the bond types we're going to be studying next unit, and that's how we primarily use electronegativity differences. But I wanted you to know the trend that existed on the periodic table. Okay, yes?
How do you know, like, if nitrogen or bromine is more electronegative?
Okay, level takes precedence always. When you add an energy level, that supersedes anything going across can do. So bromine would be lower in electronegativity than nitrogen. Going across, does that answer your question? Yeah. Okay. Yeah, level takes precedence. He was asking of a comparison of these two. This one's below, but it's to the right. level takes precedence. The fact that's on 2 energy levels below makes it way less. Okay? All right. Ionization energy is the most important one because they just love it in the AP world. I hate it, but it's a necessary evil, and it's really not that bad. I get concerned about students and their fear of it. I don't want you to be afraid of it. I want you to embrace the ionization energy. It's the energy required to remove an electron from a gaseous atom or ion. Forget this whole gaseous thing. Yeah, whatever. You don't have to focus on that. The values that have been calculated like these were done with these ions in gaseous states. Doesn't change the way you do the problems. So it's the energy required not only to remove an electron, it's to remove the most loosely held electron. All right, so can everyone see how that is removing an electron? X going to X plus E minus. Yes? That's not a rhetorical question. Do you see that? Yes. All right, so I need you all to be able to write an ionization energy representation in this way. It's just something yields something plus its electron, and this something now is going to have one up in charge. It's going to be higher up in charge because it lost an electron. So this series right here is a really cool little thing they do all the time, and I think it's an interesting way to ask questions. But they are doing successive removals of electrons. So obviously, to take an electron away from something is going to take some energy. So we have to put energy into the system. So it's going to be a positive value. And here, looking at magnesium, look where it is on the periodic table. This is removing the S2 electron. All right? 735 kilojoules. I don't know how hard that is, whatever. Do you think it's going to be harder or easier than to remove another electron? Harder. Harder. Remember, we are now positively charged after we remove one electron. Wouldn't it be harder to then remove another electron? That's going to be tough. So yeah, it does take more to remove that second electron, and this is the removal of the S1. Why all of a sudden, when we remove the third electron, whoa, look at that jump. What does that mean, Kinsey? Yes, you are now removing an electron from a closer energy level to the nucleus, and Alex said it as well, you're removing a core electron. So a lot of times they'll ask you a question, why is the third ionization energy of magnesium so high? You're going to say, because you're removing a core electron. And it's because it's now a P6 you're taking off, right? What's a really cool thing that can be done with these, and if I were writing a question on this, I would do it, just give you a list of the first 5 ionization energies of something and ask you what the oxidation state is. Look at this. What is magnesium's most common oxidation state? Magnesium. +2. What it is it's going to remove as many as it can before it takes a ton of energy. This is not energetically favorable. So this is why magnesium is a +2. It's this reason. This came first. Okay? So if I gave you a list and there was a jump between if there was a jump between the third and the fourth, what would the oxidation state be? +3. Okay? So it's just interesting to be able to do stuff like that. So now let's talk more about this trend because it's horrible. In general, as we go across the period from left to right, the first ionization energy increases. Why? Go back to nuclear pull every time you do a problem. As you go across the table, nuclear pull increases. So doesn't that mean it would get harder to take off the last electron? Right, that makes sense. As you go down the table, what's happening? Nuclear pull's decreasing due to increased what? Shielding, right. So it's easier and easier. Francium's like, fine, take my stupid valence electron. I can't even see it. It is very far from the nucleus, so easy to remove. So ionization energy decreases as you go down the table. Okay? Here is a graph. Let me make it a little bit bigger because I want you to be able to see this. Of all the ionization energies as you go across just through the whole periodic table. So it kind of makes sense. Starting with level 1, hydrogen to helium. That works. Why did it drop going to lithium? Yeah, because we went to a second energy level, so this should be lower than this. This should be lower than this. Now, there's some issues here I'm going to address, but for the most part, as you go across each period, the ionization energy is increasing, right? And then the whole decrease thing is showing up here as you go down the table. What's bad news bears for all of us are these little bitty dips. Can you all see them? Right here between beryllium and boron, that went down. Between nitrogen and oxygen, that went down. Again, magnesium and aluminum, it went down. Is there a relationship between beryllium and boron, magnesium and aluminum on the periodic table? Aren't they like right below each other? Phosphorus and sulfur. See how that's right under nitrogen and oxygen? So we're finding a pattern of where these exceptions occur. Once you get down here into the D's, crazy stuff happens, but there still is that other exception again for selenium and arsenic right here. Anywhere beyond here, our exceptions are crazy, because D's are crazy. You saw that in those videos yesterday, all those D's causing color and magnetism and all that stuff. They kind of do the same thing with the trends. But we do need to be able to explain why we're seeing some very clear patterns of exceptions. And so that's what we're going to do in this next slide. Why are there exceptions? So let's compare. I'm going to just do nitrogen and oxygen first, because I think it's the easier one. And what I'm saying for nitrogen and oxygen is for the next two groups down as well. Everything I'm saying applies to all of those. So the way you answer a question like this, if you're asked, I always say for you guys to do your electron configuration and spin diagrams first, because once you can see it, you'll remember the reason. So nitrogen has a 2s2 what? 2p. Hello? 3. And then oxygen is a 2s2, 2p4. So if the trend were normal, let me go ahead and just draw this real quick first. I'm going to draw out my spin diagrams for each, because I think that helps you see it. So we've got this. And you can answer your question like this, and the graders would love it because they understand what you're saying. So the last electron in question that we're trying to remove are those. Does everyone get that? Okay, so if the trend were correct, this electron should be harder or easier to remove? Should be harder. Should be harder to remove, but is easier. Why? Any guesses? It's more, what's more stable? What? Okay. Half-filled being stable is correct, but it's not a reason, because I can say, well, why? If I keep asking you why, it's not enough. Why is a half-filled orbital more stable? Why does that electron, and rather than thinking of what it is after you remove it, let's talk about why it's going to be removed, why it wants to be removed. Why? Because it's sharing, and sharing is caring, I thought. What I heard it, repelling. There are additional repelling forces in this P than there are here. This has less repelling forces, so it's going to be harder to remove. This electron should be harder to remove, but is easier because of repelling forces. If you draw the picture, this is literally all you would have to write. If you don't draw the picture, you'd need to say the last electron in nitrogen or oxygen should be harder to remove, but it's easier because of repelling forces in a p orbital. You have to be really specific. I think it's just best to draw it out so there's no question about what electron you're talking about, what orbital, any of that. Okay? So this is going to be the same for P and S and AS and SE. Are we good with that? You ready to do the other exception, which is kind of weird, and you're going to be like, well, that contradicts what you just said. We good? And I can't bring this down anymore. Why is that? That is horrible. Oh, well. I'll make a little barricade. Okay, so now we're going to do the other exception. Who remembers what it was? Between beryllium and boron, and what's under it? Magnesium and aluminum. So these are the only ones we need to worry about for that exception that comes across first. And this is a 1s2, and this is beryllium. And what's boron? 2s2, sorry. And what's boron? 2s2. Why y'all like not saying anything? You should know the electron configuration for boron. All right. So this guy versus this guy. Bam, 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 bam. Again, we're comparing those two. This electron should be harder to remove because, harder to remove, but it's easier. Okay, if anyone gets this and remembers this from pre-AP, I'll be pretty dang impressed because you did do it in pre-AP. Any ideas? I know it looks contradictory because you're like, well, there's repelling forces in the S. That one should be easier. Yeah. You're not. No, are you dropping a level? Those are on energy level 2, both of them. No. Because what? Well, yeah, we know that. That's why we're saying it's easier to remove that than that. That's a good idea. Does it favor a certain charge? I like that idea, but it's not. And I don't expect y'all to have remembered this. I'm going to tell you now, and now you'll remember it. It has to do with the shape of the stupid orbital. This is the 2s orbital. If this is the 2s orbital, the 2p would look like this. What can you tell me about the average distance that the electron might be from the nucleus in the p? Do you see how on occasion it's going to be further away from the nucleus, that electron? So its average distance from the nucleus is a little bit larger, making it easier to remove. So should be harder to remove, but it's easier because of the shape and proximity of the p orbital from, I'm out of room, the nucleus. Does that make sense? No? Yes? Okay. No questions about it? Yes?
Does that mean it's like easier to like go away from that one and go to the other one?
It's not going anywhere. It's literally, in ionization energy, we're just taking this electron away, and we're taking that electron away. Which one is easier to do? This is not going in. We're just taking it out.
And is that because it's like a farther?
Because on occasion, it's further away from the nucleus. So if you're further away from the nucleus every once in a while, your average distance from the nucleus is greater. So it's just easier to remove. Okay? All right. You ready for the last one? It's a long lecture, I know, but it's the last one of the unit. And to be honest, this is my least favorite of all year. So it's all looking up from here. Oh, and we have to answer these first. Which atom would require more energy to remove the most loosely held electron? Sodium or chlorine? Chlorine. Why? Chlorine. Thank you. Higher effective nuclear charge. Nice. So do you see how this test might be kind of hard? It's not that the stuff is hard, it's your ability to explain the stuff. Okay? Which atom would require more energy to remove an electron? Lithium or cesium? Lithium. Why? Less shielding. Li has less shielding, or you could say less nuclear pull, or you could say less distance from the nucleus. That last electron has less distance from the nucleus, whichever. And the last one, which has the larger second ionization energy? Lithium. Why? removal, nope, almost close, Alex. Removal of the second electron is a core electron, is removing a core electron in lithium. So it's going to be really important to get straight in your head when the exceptions, which trend the exceptions go with, and which one is which. I get a lot of students when I say B, E, and B, the first thing they do is like, oh, it's that's an exception, less repelling forces, because they just memorize it. No, it's not the one without the repelling forces, it's the other one. If you draw out your little orbital diagram, hopefully you'll see that. Okay? Now we're on our last trend. This is the craziest trend ever. I don't know why it wasn't thrown out of the curriculum. I'm going to teach it, but they rarely used to test on it. We'll see how much they test on it now. But electron affinity is the energy change associated with the addition of electron to an atom. So it's kind of like the opposite of ionization energy. Okay? What's crazy about this, it's the only trend that we take into account the negative or positive energy like we do in thermo, as in we have to put in energy to make it happen, or energy is released when it happens. So we have signs associated with this. So that's what makes it confusing to students. But any question you get will be very clear as to what we're looking for. So first let's talk about, don't look at this right now, just look at periodic table with me over here. As we go down the periodic table, we get to francium, right? If we were to add an electron to francium, do you think francium wants another electron? No. Francium has a ton of shielding. Francium has very little electronegativity. Francium's like, I don't want that freaking electron. I'm actually trying to get rid of my electrons. So if we were going to make that happen, energetically, what would we have to do to francium? Add energy, add energy, add energy. That's endothermic. So as you go down the table, electron affinity becomes more positive. Does that make sense? All metals are going to have a positive electron affinity. I challenge you to find a negatively charged metal. You can't. You're not gonna. So all metals are going to have a positive electron affinity. The question is which is more positive and which is less. Okay? So let's talk about the other way. Let's talk about as we get to the floozy. Do you think we're going to have to work at all for the floozy to take the electron? No. It's super, super, super easy. So easy that we don't do anything. So easy that when the floozy gets the electron, she's like, woo! And energy is released. Energy is released. And you got to think about it. If one way is true going down the table, the other way has to be true going opposite. So if energy is absorbed in that process down, energy has to be released if the opposite is true. Okay? So because energy is being released when that happens, what happens to the value? More negative as you go across. So it becomes more positive as you get down and more negative as you go across. All right? So let's put all our wonderful knowledge into practice for this problem. Arrange the elements, oxygen, fluorine, and sulfur, according to increasing ionization energy. Which has the lowest ionization energy? Level takes precedence. Sulfur, oxygen, fluorine. Nice. Atomic size. Yep. Do you see how that's opposite? Which makes sense because the smaller it is, the more the nuclear pull, the higher the ionization energy. Okay? You will not get questions that are this simple. This is just to make sure it's in your head right. You will always have to do some sort of explanation. I can promise you that. That's what Chem 2 is versus Chem 1. Briefly explain each of the following statements. The atomic radius of Mg is smaller than Ba. Mg, and I want you to answer the question from the perspective of the one they're talking about. Don't start talking about Ba. Let's talk about Mg. Mg what? Mg has less shielding. That would be a perfect answer. You could say Mg has less shielding, Mg has less energy levels. Either one of those is fine. Uh-oh. The ionization energy of S is lower than P. Uh-oh. S is 2s2. Oh, I always do it wrong. S is 2s2, 2p4, and this guy is s2p3. So this last electron should be harder, but it's not. S is lower. It's lower because, why? Yep, this is the electron repulsion one. Imagine your 3 boxes here, and you got that 4th one doubled up in the first box. Lower due to repelling forces in the p orbital, or in a p orbital. Good? All right. Next up. The energy required to remove the 4th electron in aluminum is significantly larger than the 3rd. Removal of the 4th electron. Do you see how I'm starting all these? Oh, 4th electron is what? Is removal of a core electron. Removing a core. That's all you have to say. That's it. I don't want to read. I don't like reading. Don't make me read. Last one. This is just a generalized question. The energy change associated with gaining an electron, the electron affinity, is positive for some atoms and negative for others. Some atoms have to what? Have to, right, so they have to basically be forced, right? Some atoms have to absorb energy, like Irene said, or be forced to take an electron. And then in the parentheses, I'm going to put that's positive energy. Some readily accept electrons and release energy. And then what is that? Negative. Negative energy. Okay? So a lot of success on this test hinges on your ability to work through problems on your own. I can stand up here for the next 5 days and work problem after problem after problem, and some of you still wouldn't do well because you're not facing the fear and writing the words out by yourself as if you're in a testing situation. So you have got 4 in-class problems next that are all AP problems. This one, this one, this one, and this one. This is what you need to do in preparation for the test. You need to go through these and work them. Okay, they're not graded. I'm not going to know if you did these or not. And I really don't care. I care, but if you don't do them, I'm sorry. You're not going to do well. So I'd like you to do these. The answers are in 2 places on the website, in the homework solutions, and they're actually in the on the very first row of items underneath Unit 5. It's also there, and then it's like answers to last 4 in-class problems is what the document is titled. And so work them on your own. Try to do them with nothing in front of you, and then go and check your answers. Don't do this the night before the test, okay? Try to do it over the weekend, and come ask me questions on Monday, because your test is Tuesday. All right? That way I can clarify any weird things going on in your head. So part of class Monday, I'm going to be like, okay, questions on those problems, and I want you to ask those of me, okay? Because there's really no reason y'all shouldn't just spank this test. It's really not tricky. It's all very straightforward stuff. It's pretty black and white factual, you know, so you just need to know how to phrase things. All right, that is all.